How you all doing this afternoon, evening for some of you? I'm doing well. Thank you for asking. Alrighty. So, just a reminder, here's my email address. There's my address for my office hours scheduling. Today, we are going to be talking.
Recording started.
About a little bit of thermodynamics and fluids. So somewhat unrelated concepts to thermal and fluids. And also something you've talked a little bit about in chemistry with thermodynamics. So we have that as well. Although we're going to be talking about what's called physical thermodynamics. There they talk about chemical thermodynamics. So, without further ado, let me ask you this question. I'm going to grab a perfectly birthday-looking pan. What is your friend saying about this pan when they say, careful, that's hot?
Presence in the facility. Cruz says he is a proud member of the jail's largest gang, the United Blood Nation. 100%.
Okay, it has a high temperature? Is that the only thing they're saying? Okay, he confirmed you.
He claims to have been a blood for upwards of 20-some-odd years.
Don't touch the pan, right? And I like what Veronica's saying there. It's hotter than your hand.
Bloods have formed dozens of subsets.
Hotter than your hand. If it's hotter than my hand, what does that mean if I touch the pan with my hand?
Some of the younger members either don't know it or don't respect you. I don't like it.
I'll get some heat to transfer from the pan into my hand. So, yes, it'll cause me a burn potentially, but the key there is that this tells us straight up that energy will move from the pan into my hand if it's hotter than my hand. And it also brings up a couple things like, okay, what's temperature, what's heat, and what is energy when it comes to all this. And that's really what we're getting down to is what's the difference, the subtle, in a lot of cases, difference between all those. First off, heat is a transfer. If I say heat, I'm not talking about it being hot. There's not, like, heat is not a thing, it's not a measurement of a thing that a substance has. It's the transfer of energy in the form of non-mechanical energy from its system to its environment. Meaning we're not talking about velocities or things like that. We're talking about simply energy going from point A to point B. And it's transfer. I can't stress that enough. Transfer. Just like work is a transfer of energy, so is heat. And we say it's an extensive property. So a bigger object can have more heat than a smaller object. In fact, if I look at my hand as a certain size, and I have a little itty bitty tiny block of metal, that tiny little block of metal, even though its temperature might be higher than my hand, is going to have more or less heat than my really large hand.
Some veterans on staff say later.
Yeah, it very well could have less energy than my hand because my hand being larger mass and that little tiny little block of metal being a smaller mass means there's plenty more energy that my hand can contain than the object itself. So the size of the object will matter here as well. More stuff means more potential energy. It doesn't necessarily relate to density per se because it does in a roundabout way, because if I have a very dense object and a very not dense object that are the same volume, then the dense object has more mass. So it's really about the mass that's contained there, not the size of it. No problem? And then let's compare and contrast that with this thing we think of called temperature. And temperature is the measurement of thermal energy, and it's basically the equivalent to the kinetic energy of the molecules, especially if I'm talking about a gas. Like an ideal gas, like you might talk about in general chemistry. So the faster my particles are moving, the more temperature the higher the temperature will be. In fact, it's 1/2 mv squared average v squared, or this other form of the equation, which you don't really have to know, which is 3/2 a constant, Boltzmann's constant times temperature. The difference, this is an intensive property. So I could have two objects, same temperature, One of them may have more heat, one of them may not have more heat. The objects are moving around. In fact, if you think about space, what is the heat quantity in space? There's a lot of heat or not a lot of heat energy, thermal energy out there?
It's more like a hobby. When you work, you have to find something that you like doing. You can't just pick any job because you're not going to stay there. And plus, I can't work for it all week. It's not enough money.
Now, like interstellar space where there's no stars. I'm just talking like the cold vacuum of space just out of our atmosphere. Very, very little. Because there's no matter out there, which means there's very little matter, very small mass. There's not much energy. There's not much thermal energy in space. The amount of energy that my space can transfer to me is very low. The heat quantity that can be transferred is very, very tiny. Strangely enough, the temperature of space is actually pretty darn high, even though we say that it has very little heat. Because when you're in space, those particles are very, 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 very far apart from each other. Are they going to have higher, slow? Are they going to be moving really, really fast or really, really slow?
Hackensack, New Jersey is better known for nice homes and quaint downtown shops than it is for gang activity. Gang-related crimes do occur here.
Like a fraction of the speed of light fast, because there's nothing to stop them. Caitlin, is there friction in space? Or is there a lot of friction in space? So, since there's nothing to slow these particles down, they're going really, really fast. So what energy they have means they're going really fast. So as far as average velocity goes, they're actually so they might be very high temperature, although contain very, very, very little heat, which is why I still freeze in space. So there's that distinction between temperature and thermal energy.
Because we don't know where they're coming from.
Sorry, dogs are going crazy over some cats, I think. So, got intensive property of temperature, extensive property of heat. And they do relate. They are not different from each other totally. They do relate. So if you have fire, and it's transferring heat to my water, what will happen when I add heat to the system by fire? What's the net result?
Bates has pled not guilty to multiple charges of weapons possession and aggravated assault.
I will transfer energy into that water. When I transfer that energy into the water, my molecules will go more quickly, which means I will raise my temperature. Temperature increases as the heat increases. So there's a connection, but they are two distinct things. Everybody with me? Smiley frowning.
Bates will now take the case to trial. In the meantime, he'll remain in the Bergen County Jail, where he holds a distinct status.
Right now, I do believe my face.
All right. So, what I was saying about space is in the fact that space has very little heat, but the temperature of the particles can be very, very high. There's not a lot of stuff out there, so low heat contains low thermal energy in there. However, particles move fast, so high temperature. That would be an extreme example, right? Most of the time, if I have more thermal energy, I will see larger transfers of heat, which means I'll see larger temperatures. But they can throw those really kind of extreme examples your way from time to time. Yep, the definition of extensive versus intensive properties are going to be extensive properties only depend on mass, intensive properties do not depend on mass. So that is the distinction. So the color of a substance doesn't matter how much you have, or the intensity of a substance doesn't matter how much you have. The mass is an extensive property, heat is an extensive property. What's another extensive property? Volume is an extensive property. More stuff that's going to have a greater more mass is going to have a greater volume, that kind of thing. Most of the properties you talk about in chemistry are intensive properties. Now, what happens if you want to add heat to an ice cube at 0 Celsius? What's going to happen to that ice cube? What's going to happen to that ice cube's temperature? Nobody's gotten this one right just yet. No change. Actually, the temperature does not change. I will see a phase change. The phase changes from solid to liquid, but the temperature remains the same. So it's going to be melting and turning into water at 0 Celsius. And then once all the melting process has occurred, then the temperature of the water may go up. I'm not sure if you've had GChem class, I think it's class 3, where they give you this diagram. This is a heat diagram. You add heat, and this is the temperature axis. We're talking about going through this phase change, this horizontal portion. So all of the heat added goes into doing what? Increasing the velocity of the molecules or breaking bonds between the molecules. During my phase change, all I'm doing, all heat, breaks bonds. Not while I'm doing the bond breaking. All the heat during a phase change is pulling those molecules apart from one another to go from the solid to the liquid phase. It's not until all of those bonds are broken where now all of the heat goes into speeding up the molecules. So you're going to get two different things going on in here whenever you're doing these phase changes. So you got to remember that heat doesn't always increase temperature. Taking away heat doesn't always decrease temperature. Phase changes, all of that energy goes into breaking or forming bonds. Is everybody with me? Smiley frowning. That's the same deal if I've got 100-degree water and I'm going to convert it into 100-degree steam. That's just the phase change where there's no temperature change. And it's not until it's all completely boiled where the temperature of the steam will start to increase. So the heat goes into either breaking bonds or speeding up molecules. Make sense, Danielle? So your GChem teacher, by the way, should corroborate that as well. Because if you haven't had that class, they're going to talk about the exact same thing. So let's try a multiple choice question. A, B, C, or D. Use the polling feature up top. What do you think about heat versus temperature for a glacier, a red hot piece of charcoal?
Over a period of 26 years, crews have spent time not only in Bergen County, several other New Jersey jails and prisons, dozens of convictions. They include assault, distribution of drugs, burglary, illegal possession of firearms, criminal sexual contact, endangering the welfare of the child.
If y'all would have came in here last week, you would have saw me over in that corner smoking my weed. But this week I ain't got no more, you know.
So it looks like we're getting bifurcated as a class on this one.
He's pled not guilty.
Normal. We're picking either between A and C. So let's approach this a 2x2 way. Which one do we know has the higher temperature?
Give me a blade or a burner.
If it's red hot versus icy cold, we know that B and D can't be correct. The charcoal has to have a higher temperature than glacier. But it's a huge glacier versus a tiny, teeny little piece of charcoal. Who has more thermal energy? As the sheet is saying, since the glacier has a huge mass, relatively speaking, remember, mass is going to control how much heat I can contain. More stuff means more heat. And especially since they're kind of going huge versus very small, we can say the answer to this question is going to be C. Actually, C, not A. So the distinction between temperature and heat.
Like 6'5", 6'6". Mr. Cruz won the fight.
Alrighty.
He did a lot of damage to the other person.
So let's talk about how heat gets moving around, how we transfer heat from place one to place two. And this is actually what we call Zero's law of thermodynamics. It was come up with after the first, second, and third laws. And so basically, what the Zero's law of thermodynamics tells us is that when you've got two things in contact, they will reach thermal equilibrium. So if you put hot water into cold water, what do you get?
You don't even have to ask me. I have to go to the hole, right? It's like, you gotta go to the hole, okay? But no handcuffs.
I basically wound up taking them down to the hole by myself, and we had an open rapport communication system.
Warm water, normal water. So that's the idea of thermal equilibrium. When you mix the two together, they will come to the same temperature and share their heat.
To kind of presence in the facility.
Cruises.
Yes, Bridget, that is correct.
United Blood Nation.
That is correct. Alright, so there's three ways that things can come to thermal equilibrium. There is conduction,
He claims to have been
there is
upwards of 20-some-odd years.
convection,
He's used to hold a lot of weight in the gym. As of right now,
and there is radiation.
Since Cruz's younger days.
So can you think of an example of heat conduction?
Even causing confusion among themselves about who's who. In Cruz's case, some of the younger members either don't know him or don't respect him.
I don't like him. My man right here, San Fran.
Totally touching the hot frying pan. Friction, I think when you think in terms of friction, it would be if I'm holding the object that's experiencing the friction, then my hand in contact with the hot object, I'm conducting heat. It's basically coming from the two solid surfaces in contact with one another. Two solid surfaces in contact with one another. Or if I put my hand on my dog is always like feels like it's 1,000 degrees. That's conduction because the heat is going from his body into my hand. What's a good example of convection?
They're our neighbors and our friends, and we're all going.
Fine, I'll go. Only because I like playing with that awesome baton collection they keep under their bed.
Sam, just watch your hands.
Okay, boiling water. So you're talking about heat within the water, right? So you got the water at the bottom gets hot, and so the top of the water is going to get hot after the water goes up into the pot, or like circulating convective currents. Anything biological you can think of? How do we move heat around the body?
Thanks for picking up the shower gift, Roger.
Totally, blood. Blood is basically a forced convection system because it picks up heat in one part of the body and drops off heat in another part of the body. So I've got some kind of fluid circulation there. So the states of matter involved in convection are not solids. What states of matter are going to be here?
Mind-blowing furniture. Spectacular people who look like they all must have passports.
Liquids and gases. Those are fluid forms. Liquids and gases are what are going to transfer heat via convection. And then there's radiation, which requires no medium because what's happening in radiation? Energy is being transferred how?
Environmentally friendly, and your lead driver. It's incredible. Sorry. But tell me, lead driver, why are you still wearing it inside?
It's just part of my
Not electrons. There's literally no matter involved here. Absorption of light waves. Yes. Electromagnetic energy. Heat transfer by emission or the absorption of electromagnetic energy. So I can absorb the light rays from the sun and it feels warm. Makes me feel all kinds of warm. What's the type of radiation that's most associated with heat transfer? I would call gamma the type of radiation that's most associated with death. I'm assuming yes, it can also transmit heat, but it would like just burn me to a crisp. I would like be Swiss cheese. And not actually microwaves. Surprisingly well. Good thing not microwaves because my cell phone works with microwave radiation. So otherwise I'd be cooking my brain. UV, electron transfers. See, how many help you out here? IR, infrared. Like when you're looking through those thermal imaging goggles, what those thermal imaging goggles are picking up is infrared radiation. So hot objects emit IR radiation. And if you look at a snake even has an IR sensor. Not all snakes, but many snakes have a little pit in their forehead, the pineal eye, which actually detects infrared radiation. So it can tell where the hot objects are right there in front of it. So 3 modes of heat transfer. So why then is my oven mitt a useful thing when I'm cooking? Yeah, it prevents heat transfer. I like you guys using the terms too. It prevents conduction of heat because it's insulated all the way to my hand from the fan. There you go. IR is long wavelength, guys. We're going to do this later on in class, but might as well put it down now. The electromagnetic spectrum goes, I'm just going to give you the first letter of each one. You go from radio waves to microwaves to IR to visible to UV to X-rays to gamma rays. I'm going to spell this out a little bit more. Radio, micro, infrared, and so on. So IR is on the low end of the spectrum, low energy end of the spectrum. Sarah, question?
Wake up. You've been down here all night.
Not that it transfers the most heat, it's that this is the one that's associated with heat. If I've got hot objects, they radiate, they will the molecules that vibrate will emit infrared radiation.
Michael, it's us, your new parents.
Oh my God, he's perfect!
They'll emit infrared photons, yes. And it's not about the wavelength that it has less energy, it's going to be the fact that IR is what's emitted. So you're not going to emit gamma rays or X-rays from hot objects. You're going to emit infrared and then ultimately possibly even visible wavelengths. Because if you see like red hot, like we talked about that piece of charcoal, red hot because it's emitting red light now because of the heat it's exhibiting. So heat is down here. This is electron transfers, this is heat. So different wavelengths of light are coming with different types of energy. Okay, L. I can remember that one because the new movie, or not the new old movie coming out. Alrighty. Now, let me ask another question. If you add heat to something, what are the possible effects? And we already know one, or two of them. I'm just going to put them up here. Phase change and temperature change. What else could happen?
Sweet dreams, Angel.
Entropy change.
This is my home now. Yeah? What are you gonna do with the actual
I'm going to leave velocity change to be in under temperature change because it's the same thing.
Right here, honey. They have big plans for me. By February, I'll have mastered
You're thinking very chemistry. You think more physicsy. Phase change, temperature change. Wonderful little chemistry equation to help us think more physically. Pressure change. Volume change. In fact, if we pull energy change out of here, these all go into an entropy change. All of these would be associated with some kind of entropy change in some way, shape, or form. So if I heat up an object, I can achieve all these different things, and a lot of times the question is, how do we know which one's which? And to do that, we have to understand the first law of thermodynamics, the law of conservation of energy. This is a different version of this you've probably seen before. Well, you've probably seen it, but it may be that this was actually a plus. Our sign convention that we're going to use here in this class is going to be delta E equals the change in internal energy is equal to the heat transferred minus the work done. Heat transferred minus the work done. It's actually the same equation, it's just a different sign convention. So really it's not about knowing when to use one or the other, it's just making sure you are consistent with your sign convention. Because it's literally the same equation, except I would flip-flop the signs of W. So let's see what this sign convention is. For heat, this one makes sense. So it's Q, that's the heat added to the system. So if I'm putting energy into my system, what would Q be? Would it be positive or negative? Positive. If I'm taking heat out of the system, i.e. cooling the system or putting it in a refrigerator or freezer, what would Q be? Q is going to be negative. The work is the one that's confusing because in chemistry we define it, it's not the work done by the system, we define it in terms of work done on the system. So that's what changes the sign convention here for work. So in chemistry class, you almost certainly learn this as Q plus W. In a physics class, you would learn this as Q minus W. Honestly, it doesn't make that much of a difference as long as, again, you know your sign convention and you keep track of that correctly. So if it's work done by the system, like i.e. the gas in a piston lifts up the piston, what would work be? Positive or negative? If I lift the piston, would my work be positive or negative? It would be positive because my gas in the piston is lifting, it's doing the work. The gas is the system. Usually when you're talking about, most of the time when you're dealing with physics work, you're talking about a gas doing something. It's a gas / liquid in a refrigerant system. It's the gas inside a piston. It's the gas inside a balloon. It's the gas inside your lungs. The gas itself in a piston is the thing that is the system itself. All the other parts, the machinery, the mechanics of it, is the surroundings. Yeah, thank you, sir. Work on the system is not positive in this convention. Work on the system is negative in this convention. This is work done by the system, which is positive. So if I have a piston sitting in this cylinder,
lazy boy, and he convinced Greg to go along with it? I didn't throw an orphan out of an airplane just to have Terry drag me back to a life of unsophistication.
And I have my gas molecules in here, and as this piston is being lifted up, the gas is the system, which means it's expending energy to do this, but we say work is greater than 0. The gas is doing work on the surroundings, and that should be a total loss of energy from my thermal energy in the system. And it is, because if work is positive, delta E would go down. If work is positive, delta E would go down. It's not the system because the system is defined as the gas itself. And that's the thing. You've got to isolate yourself into what is defined into the system with all these problems, and the gas is the system, not the machinery, not the mechanics. It's the stuff that is doing the work. And the gas particles are what are going bam, 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 pushing this piston upwards.
Going through, talking to somebody, find out why this happened.
Got it, Trevor?
Want to make sure
It's by definition.
sun never gets pushed out the window again, never gets boiling liquid poured on them again, then you can't be.
And like I said, in almost every sense of physical thermodynamics, it's going to be a gas on the MCAT. Heck, in most classes that you take, it's going to be a gas. So the opposite convention is when work is done on the system, then I'm going to have negative work, because that would be like me
You know what? This story started out.
crush, like pushing down on the piston. Or if I take a balloon, there's gas inside this balloon, and if I were to shrink that balloon, if I were to compress that balloon, that's negative work because the gas is having work done on it. So I think your biggest challenge in these types of questions simply revolves around the fact that you got to keep your sign convention straight. Many of you guys, the last time you've had exposure to this was in general chemistry, where it was the opposite sign convention, Q plus W. But reason it out, you can still get to the right answer. Everybody with me? Smiley frown. Rebecca, is that a question? Yes, there is. We're always talking in terms of the system. Yes. No problem. So ideal gases, like I gave you guys the ideal gas law, it's very common. Make sure you're also thinking about the ideal gas law in physics when you're talking about gas pistons, gas-filled balloons, gas-filled that, gas-filled this. PV equals nRT. So I'm going to leave that to your G-Gun teacher to teach you, but that's the equation we do need to know. And that's because many of the problems are going to have, like they're going to use volumes and temperatures and pressures and entropies and all that kind of fun jazz. So you can't divorce this topic completely from GChem. In fact, we used to teach this in GChem, not physics. It's only because our classes got compressed that we transferred to physics. All right. So, oopsie. Didn't work the way I wanted it to. Okay, there we go. All right, so what we often will do is with these problems involve a PV equals nRT diagram or a PV diagram. Pressure on the y-axis, volume on the x-axis. We can see here we go from one set of conditions to a new set of conditions. The one variable we cannot visualize with this is temperature, although anytime you're doing a pressure or a volume change, you're often going to see a temperature change as well. So whatever the conditions are, if I'm going from one point to another point here, I'm always going to see delta E be the same whether I go this route or if I said like went all over the place to here. Thermodynamic quantities like delta E are state functions, which it means no matter how I get between the two, you get to the same exact conditions. So the delta E for this transition is the same as the black transition. And there's four reversible pathways that we're going to have to understand. The first of those is, well, here are the four: isobaric, isochoric, adiabatic, and isothermal. So what does isobaric mean? Whatever the transition I'm doing is going to be constant pressure. delta P is equal to 0. So on a diagram like this, what is that going to look like? Is that going to look like a vertical line, a horizontal line, a diagonal line, a curve? It's going to look like a horizontal line, because if its delta P is 0, that means straight across. So here's an isobaric process. If I take a weight and put it on a piston, the gravitational force down is going to equal the force of the and the force that that gas can push upwards with is defined as its pressure. So the pressure is equal to force on a surface divided by area. Force on a surface divided by area. It has a unit of Pascal, which is a Newton per meter squared. A good conversion for us to know is that 1 atmosphere is equal to 100 kilopascals, which is equal to how many pascals? $100,000 pascals. 100,000 pascals. So we can set up in a relationship that says the force is equal to pressure times area that my particles are providing, and that's going to equal the mass moving downward. That's going to be my equilibrium situation, my equilibrium conditions. So if I start putting heat into this gas, what's going to happen? Well, if this is an isobaric process, the pressure is not going to increase. Because it can't. The isobaric process is isobaric because we have to have thermal equilibrium here. Whatever the force is up has got to equal the force down. So pressure here must be constant. So if the pressure is constant, what other variable needs to change? The volume can increase. The volume can increase. The gas will expand. And so you said we would increase, or we would do work on that gas. Or at least would it be the gas doing work, or would it be the system doing work? Or sorry, let me rephrase that. Is the gas doing work on the piston, or is the piston doing work on the gas if the gas is expanding? The gas is doing work on the piston, it's lifting up the piston. And that amount of work is going to equal the pressure times the change in volume. The pressure times the change in volume. And yes, Weston, it is definitely positive. Because the work is going to equal the force times the change in height. That force we know is PA, and the change in height, that's just D. So P times area times the height is equal to volume. So work is equal to P delta V. They'll give you some way to determine that it's isobaric, but it isn't a bad idea to simply know that if I've got a piston that's being heated, this is an isobaric process. This is the most common example of isobaric processes. A gas that's lifting a weight. A gas that is lifting a weight. And how does that appear on my graph? What is that going to look like? Horizontal line. Pressure is constant while the volume is increasing. Volume increases, pressure is constant. So overall, my delta E for this system is going to look like Q minus P delta V. Q minus P delta V. So the heat goes into increasing the volume. All right. What's another type of system I'll run into? What does isochoric mean? Isochoric means constant volume. Isochoric means constant volume. So let's look at a constant volume type process. A constant volume type process, you could say isovolumetric or isovolumeric, but that one's a pretty big giveaway. Isochoric is the weird one. So they're probably not going to use that isovolumetric or isovolumeric just because it's too quote-unquote obvious. So if I lock the piston in place and I start adding heat in here, what's going to happen? I am going to increase the pressure, but what am I not going to do? What must equal 0 if delta V equals 0? I can't do any work. There's no way to do work. The piston won't move up, the piston won't move down. So since delta V is 0, work is thereby 0. Which means all the energy that's going into the system is going into raising the pressure and also doing what else? If the pressure goes up, the delta E goes up, and we see that delta E equals Q. All of the heat goes into increasing the internal energy. And by the way, in a general sense, if you're just thinking in general terms, you can always use delta E as kind of a measure of delta T. If delta E is positive, delta T is also likely going to be positive. Great example of this is like when I go camping and I want to cook the beans, the can of beans that I bring with me, I just put the can of beans right in the fire. I know they're the right temperature when the can's top just goes right off. It pops right off. And it does that because inside, not only is the temperature going up, the pressure is also increasing. Cook baked beans in a fire. Oh yeah, it's awesome. Jackie, question? That's right. If the volume, not V, but delta V, just to make sure, delta V is 0 because there's no change in volume. 0 times P is just 0, so delta E is just going to equal Q. So another way I also try to, I always remember isochoric is that it's 0 work because it's constant work. Like choric makes me think of chore. So this is my chore. If it's isochoric, then I have no work being done. So in fact, that's a nice little way to remember this process, this relationship is that isochoric means work equals 0. Work equals 0. Sarah, question? I'm saying that delta E and delta T are essentially equivalent to each other. If delta E goes up, delta T most likely went up as well. If the internal energy goes up, then the kinetic energy goes up, the temperature goes up. Bridget, question? Just realize it's an approximation. just because heat goes in does not mean I'm actually going to change the temperature. In this case, yes, I am going to change the temperature because heat goes in, and the only thing it can do, because it's isochoric, is change the temperature. But heat does not have to change the temperature. Heat can do all kinds of things, like we said, which is do a phase change, or do a temperature change, or do a pressure change, or do a volume change. We're talking about all these different conditions where we're going to see it do different things. Current process, yes, the thing that the heat's going to do is increase the temperature in this scenario. And what would my graph look like for this guy? This is going to be a vertical line. This is the vertical line. All right, what is my next type of transition? Isothermal. What does isothermal mean? Constant. This one's the quote-unquote easy one. Constant temperature. Constant temperature. So something that would be in a constant temperature scenario would be putting something in a constant temperature water bath. So if my constant temperature water bath is here, it is transferring heat in. Heat is being exchanged between the water bath and this. So if the piston is lifted up, what's going to happen? If I lift the piston up right now, what's going to happen? The volume increases. What's going to happen to the pressure? It's going to have to decrease a little bit when I do that. When the volume increases, what's the heat doing? Is it doing work on the gas, or is the gas doing work on the piston? It's being transferred in so the gas can do work on the piston, and that energy's got to come from somewhere. So where's that energy coming from? If it ain't coming from change in temperature, it's coming from the heat flowing into the gas from the water bath. So heat flows in to the water bath to keep the temperature from changing, because otherwise it would change and we go down. And in the end, what do I see? Q equals W. Q is going to equal W. And remember, the easy way to remember this is, if it's isothermal, which of the variables in my delta E equals Q minus W is going to be 0? If it's isothermal, and I can approximate delta E as delta T, then delta E is going to be 0. Yeah. So I can just use that equation, or that equivalence in my head, to remember that delta E is going to be 0, which means I just rearrange it to Q equals W. And that graph is going to be a curve. As the pressure goes, or as the volume goes up, what's the pressure going to do? Pressure is going to go down. And it's going to be how do I phrase it? It's a 1 over V. It's an inverted relationship. NRT is constant, so P is proportional 1 over V. The volume goes up, the pressure goes down. It's going to look like this. This is what's called an isotherm in one of these graphs. So the heat goes in, does work to keep the piston up, and there we go, isothermal process. Trevor, is that a question? I'm lifting the piston up. So the gas has to expand to push the piston up. Yes, it's pushing on that piston. It's sort of like chicken and the egg in a way. If I lift the piston up, is the gas doing work on the piston? Yes. Even though I lifted it up, the gas has to expand to fill the container. So the gas is doing work on other gas molecules to do work on the piston. So you can also see, if I just put this in the water bath, then the piston would spontaneously start to go up, in fact. It is a little weird. Just think of it this way. If I would actually take this and put it underwater in a hot water bath, the piston would lift up in response. So the gas would be doing the original origin of the work in that case. Good question. And then we have our last type of scenario, and it's called adiabatic. Adiabatic. And so what's going to happen here? This one's no heat transfer. No heat transfer is actually going to happen. So Q in this case is 0. So to put in a nice summary, all the different things that happen here, for this one, W equals 0. For this one, delta E equals 0 as well. So if you're going to be remembering all these different types of processes, I would also make sure you equate for isochoric, W equals 0. For isothermal, delta E equals 0. It makes it a lot easier to understand what's going on. So I look at my adiabatic process, and I'm going to have a insulated cylinder. Insulated, another term that means this might be isolated. And another term that means this also would be a rapid process. Because in a rapid process, is there time for heat to be transferred? And you've probably experienced this. If you touch a hot pan real fast, you just tap it. Does a lot of heat go from your finger, from the pot into your finger? Do you burn yourself? Not immediately. If I just do it quick, I just tap, and then I'm not going to get as much heat transferred. I'm not going to notice it. So adiabatic can also be described as a rapid process. A rapid process. So in this case, if the piston goes up, what's my gas doing? It's expanding, it's doing work. But since there's no heat source to replace that energy, what happens is the temperature is going to start going down. So that it is also a curve, but it's a much more steep curve, and you don't actually have to remember what that curve looks like. If I'm looking at the same sort of 2 points there, starting and ending, we all know how to break into Bradley's computer now. So what it is basically a much more steep version of the curve that we saw for adiabatic. For isothermal. They're not really going to give you any questions that make you directly say this curve versus this curve, this curve versus this curve. That's asking too much. But the more important result is here is that since Q is equal to 0, what is my equation? Delta E equals negative W. So if my gas does work, then the temperature goes down. Because remember, this again is a kind of like delta T. So 2 processes you want to be very familiar with. A rapid expansion of a gas and a rapid compression of a gas. If I do rapid expansion, what happens to the temperature? a rapid expansion, W is going to be positive, which means E is going to be negative, so the temperature will drop. The temperature decreases. If I do rapid compression, what is the temperature going to do? The temperature is going to increase. Both of these are very common processes. If you've ever used one or played with one of those cans of air, or if you've ever used what's the word I'm looking for? One of those paintball guns that uses little CO2 cartridges. What happens to them when you start firing them a lot? The temperature drops, so they feel super cold. What's going on there is literally you're doing a rapid expansion of CO2 out of a pressurized container. That's going to cause the temperature to drop. It's rapid and it's expansion, so you see an adiabatic expansion. Temperature drops. We're inside a cylinder in a diesel engine. The piston compresses. When it does this rapid compression, the temperature goes up and combusts the gasoline, or the fuel in that case, the diesel fuel. Rebecca, question? If I have a temperature increase associated with a volume increase because I'm doing it slowly, then sure, I might actually see expansion associated with a temperature increase. The volume goes up, then the temperature is going to go up. But we're not talking about that. We don't have time to do that temperature or heat exchange. We're not talking about heating the gas, which is what you're thinking about. This is just something that happened rapidly. There's no way to replace the energy. You're thinking P equals nRT? I'm not talking about P equals nRT just at this moment. I'm talking about all the energy, all the work that's being done is not being replaced by heat. You're thinking I have heat in addition to it. So there's no heat around in this type of scenario. Rashida, question? That's correct. In the case of rapid compression, the piston is doing work on the gas, which gives me negative work. Negative of a negative is positive, change the temperature.
Okay, manslaughter, it's showtime.
Alrighty. Now, there's another type of question they can ask, and that is how much work is done. They can make you quantify it from a graph. So here's my isobar, my isocore, and isotherm, and note what I said, that this is a steeper adiabat. Again, you don't have to be able to determine the difference between isotherms and adiabats visually, but I want to be able to calculate the work done by the system. Well, if work is equal to P delta V,
I've only sold 3 subscriptions.
Gotta stay upbeat, Stan.
how might I be able to use this graph to determine work?
His dad is a dentist. He's just restocking his waiting room. Okay, we're not gonna let weirdo Stan Smith spoil our surprise, are we?
Just like we did with those graphs of
Skinny jeans for Michael. I can't
velocity
wait to
and
see
time, we can calculate, or velocity and displacement, we can calculate work as the area under the curve. So what's the area under my isocore?
You don't happen to have any Spanx lying around, do you?
0. And remember, there was 0 work done.
Stop it, Greg.
So which one is consistently always going to have the greater amount of work done by the gas?
We're all gonna wear skinny jeans and no shirts for our Christmas photo. And now it's ruined.
The isobar will always do the most work. Sign convention here is very important. If I'm looking at this isobar and I put an arrow this direction, what is my work? Positive or negative?
There's something I need to talk to you about. I found these used
foil wrappers in the outside garbage. That's right.
Because I put the arrow from low to large, with a small to large volume, final minus initial gives me a positive delta V. That's going to be a positive work. If I put my arrow this direction, say on my isotherm, what's my work going to be?
I'll lose everything. We have no choice. When we talk, I have to kill Michael.
It's going to be negative because if I do that process from high to low volume, a final smaller volume minus a larger initial volume gives me a negative volume change, which means my work is going to be less than 0. So essentially, if the arrow points to the right, it's positive work. If the arrow points to the left, it's negative work.
Two of us, nobody around. Sounds perfect.
So if I see some kind of physical cycle, which this is not an uncommon thing to do, give you a process. They'll give you an arrow, like another arrow, and another arrow, sort of like this. Which two parts of this process are going to be positive work, which two are going to be negative work?
My enemy, the box spray is behind you.
The top two are going to give me positive work. The bottom two are going to give me negative work. For a grand total of...
No, turns out there was no fault.
Not 0. It might think it's 0, but not 0.
What the hell's going on?
I'm trying to kill you.
Kill me? I'm trying to kill you.
These guys are... I've got a much bigger amount of work being done by this guy than being done by this guy. So disregard the edges for a second. I'm going to the right with a big positive number. I'm going to the left with a smaller positive number. Who's going to win? The positive or the negative? The positive is going to win. Because it's literally area inside this thing. Because, Jackie, let me try to do some other color. The area under this curve is all of this, from here to here. The area under this curve is here to here. Which figure is larger? The green figure or the red figure? So, that being the bigger positive number versus the smaller negative number means this guy is doing a net positive work. That cycle is doing a net positive work. Rebecca, question?
Sarah, Roger! Oh, Stan, you saved me! Oh, flatter yourself. I came here to save Terry. Oh, Stan, I'm so sorry for the way I treated you. Please, let me come home.
Because this one is going from a smaller to a larger volume. This one is going from a larger to a smaller volume. This arrow is to the left. This arrow is to the right.
Let's hit home.
Sounds good. But first, we gotta make a quick stop for pizza poppers.
Sarah, question?
It is with heavy hearts that we inform our viewers that our adopted Russian son, Michael, tragically drowned in a mountain lake.
If you wanted to do this all said and done to truly calculate the total amount of work in the cycle, yes. But to make relative comparisons, if it's almost vertical, it's going to have very little to do with the overall amount. So, yeah, I'm not really paying attention to those because they're essentially vertical. They're not giving much work. The bigger areas are the ones that are more important. All right, so sequence of reversible processes transitions an ideal gas from P1, V1 to P2, V2. But P1 is greater than P2, and V1 is less than V2. In which sequence does the gas do the most work? So first thing you do in a question like this is just draw your points. P1 is at a greater pressure than P2, and P1 is at a lower volume than P2. So here's my initial and final state. This is 1, this is 2. start there and then try to answer the question. So A, B, C, or D, what do you think is the truth God? And there's a trap answer here. There's definitely a trap answer here. If we were talking about gravity or magnetic force or electrical force, which is the correct answer? Talking about a conservative force. D would be the correct answer. But heat, thermal energy, is not a conservative force. So let's get rid of our trap answer right away. Work is not going to be the same for different thermodynamic cycles. Never, ever, ever will it be the same. Now, it's the exact same process, it's not going to be the same way. So that's the trap. Let's get rid of D off our list. Is it going to be A, B, or C? So it looks like most of us are settling in for A. So show them all. A will do in green. So isobar would be vertical or horizontal.
Hey, Nick, damn drunk, wake up. What? Morning.
So I'd have an isobar and then an isocore, vertical or horizontal.
You'll always have a place to drink here, you degenerate.
So I'm pretty much convinced that that one right there is already my correct answer. But let's not skip steps. Isobar, isotherm.
Sign said, do not enter.
Do not enter the kingdom of heaven.
Horizontal line.
Right figure.
And I gotta have a curve in here.
It's right there.
So which one's bigger now? A or B?
Girl shoulders.
I'm Charlotte. I just moved here.
So B is out.
But I'm
Then isocore, we'll do that one in blue. Isobar, vertical, horizontal.
Wait, are you saying it's
Which one? C or A? Which one's bigger? A.
What? Oh my God, is it?
So my best answer is A here. Isobar, isocore. Just sketch them out, and you should be able to see which one has the larger area. That would be A. Everybody with me? Smiley, frowny.
So if you guys ever want to come, no Charlotte, bad Charlotte. I'm sorry, I should go.
Oh my God, you know what this means? We're gonna get laid! And the Spice Channel is still profitable.
All right. So, entropy, I'm not going to mention too much about entropy other than the fact that this definition is a little bit flawed. And that entropy isn't a measure of disorder, it's actually a measure of potential disorder in a system. And you're going to be talking about this in G-Chem class, so that's why I don't want to say too much about it yet. I don't want to contradict. But entropy is the foundation of the second law of thermodynamics, which says entropy of an isolated system, which means nothing can go in or out, it's just self-contained, either stays the same or increases. Either stays the same or increases in any process. So basically, the entropy has to go up or else, kind of thing.
I think it's fine.
I hope you don't mind me interrupting, but there is an
The only possible way you can get entropy to go down in a closed system is if that system does work on its surroundings. It does something else to its surroundings. And that means it's probably not an isolated system. An isolated system would be essentially a box in a vacuum. Something more realistic than a box in a vacuum would be, oh, what's another word I'm thinking about? What's another good example of an isolated system? Oh, essentially you can think of like the calorimeters. If I have a calorimeter, it's the calorimeter. Inside the calorimeter is a closed system. Energy shouldn't be going in or out of that thing. Well, not really. That's a really terrible example. Something insulated is about as close on Earth as we can get to an isolated system. Insulated with no inputs or outputs. So basically what we're talking about is kind of a theoretical construct. If we're talking about the second law of thermodynamics, the nice thing about it is, generally speaking, it also holds true for things that are not isolated. Because what if I were to go in the corner of the room and pass gas? What's going to happen to that gas? It's going to diffuse to the other parts of the room, push everybody away, because its entropy is going to increase. So even if it's not a closed or isolated system, it still can potentially increase the it's still probably going to increase in entropy spontaneously. So most of the time, processes are driven by increases in entropy. Most of the time, processes are driven by the increase in entropy. Now the big question is the human body a closed system, an isolated system? Why not?
Keep an eye on Betsy. She's definitely stealing from the till. So I'm tired of you accusing my wife of stealing. Meet me in the parking lot in 5 minutes. Stop watching me switch characters and call an ambulance.
Roger, you're awake.
Not in just a heat. It's definitely not isolated because I can exchange heat.
That bar gave you a heart attack.
I also can exchange gas. I also eat and poo and pee, and so that means I'm not closed system.
I brought someone to see you.
I'm not selling the bar. You better.
Breathing, food, water, all that stuff. So that's the difference between, like, I've got any kind of orifices, yes, that means I'm not a closed system. So there is a distinction between closed and isolated. Isolated means can't interact with anything. Closed system means it can interact via heat transfer, but it can't do anything else. It's closed so the gas can't go in and out. And then that means humans must be open systems. Trevor, question? The net entropy of the universe must increase. Technically, the definition of entropy is the net entropy of the universe in any process needs to increase. So if in this closed system the entropy goes down, that means the outside the system has to go up so that I have a net increase in entropy. Sarah, question? All right. Well, let's use this right away. Let's go ahead and get our ICCs out. We're going to do a passage. We're going to do passage number 6 on page 72. You got those ICCs? Raise your hand when you're ready to rock and roll.
I made eggs, coffee, and breakfast pork chops for you, Pam. He did. I saw it. I see everything.
Page 72, ICC number 6. 5-question passage. I shall give you 8 minutes to do this one. So grab those ICCs, raise your hand when you're ready to do it. Do it.
So Roger, any plans now that you're retired?
Well, I've done thing I'd like to do from now until I die, neatly filed in a bucket. Still working on a name for this bucket index. That's the index is the working title. Wow, everything's delicious. Hey! Okay, off to work. Oh, okay.
And Brigitte, Christina, Crystal, Alita, Madeline, Mary, Parker, Martis, Rosemary, Sarah, Weston. You guys here ready to do the passage? Raise your hand when you're ready to go. Passage number 6 on page 72. All right, that's a quorum. So I'm going to give you 8 minutes to do this, guys. No worries. That's why I was checking. So ICC number 6, on your marks. Get set and go.
Okay, first thing, meditation. I'm gonna close my eyes, clear my head, and find my quiet place. I'll come back to that one.
Recalling these Speedo snot. The mere sight of us must be driving Charlotte crazy. Come on.
What do we do?
What cool boys do best. Wow, the pool looks great. I really owe you guys. I'm gonna owe you so hard. Well, when you boys are done out here, why don't you, meet me upstairs?
Gentlemen, we are in. Oh, right. The Speedos worked. But you gotta get them back so I can return them to my bisexual uncle's loft before he gets home from his vacation in Croatia. Yeah, he's pretty worldly.
Sounds like they're having fun. I guess there's no reason why I can't go up there. What the hell did they do?
Hi, we've got a bit of a wait, but feel free to look at some of the crazy stuff on our walls. Peoples from around the world. Even I'm getting hungry.
Hey, look who it is!
What have you done to my bar? Everything's different.
Well, not everything. We kept the spirit of a dive bar, but got rid of the smell and the hopelessness. The guy showing his joint to all the waitresses.
But that was Nick, my most loyal barfly.
What are you doing here anyway? If I were you, I'd be out there living life, crossing everything off my bucket list.
What?
Ah! You're on fire today! Here, let me show you the new game room.
You have a game room? What the hell?
I heard some boyfriends that I was too annoying to take some flick.
Take anywhere, I would say. Being pushed out my own bar is worse than 1,000 heart attacks. It's also worse than 10,000 maniacs. But just barely. I think that's an old reference.
Roger, if selling your bar is bothering you this much, maybe you should try to buy it back.
Oh my God, I totally should. I'll buy the bar and put it back the way it's supposed to be.
It's the third house on the left. This is your house? I don't think we should leave it here.
He'll be fine. There's police everywhere. Plus, he's got a snorkel. Right. The door will shut on its own. It's not closing. I don't know. Maybe you got to turn or something. Don't slow down. Forget it. Just drive. It's not hurting anybody. Hey, what are you doing out here? They won't let me in the bar, Raj. This changes now. You will be served again.
Thank you, Roger.
You're welcome. Thank you.
Thank you so much.
You're welcome. Thank you. Thank you.
Yes, thank you.
Well, I'm still here and I'm not inside. Please, take care of me. Toby, you've destroyed my vision. I'm here to buy you out and put everything back to the way it was.
Oh, shoot, that's too bad because we're expanding Roger's stuff nationwide and we wanted your beautiful mug to be the face of the company.
Right, that's what we're doing. What did I say? Thank you, Toby.
Yeah, you're welcome.
Thank you.
Of course.
So much.
Said you're welcome.
Seriously,
Okay,
thank you.
Roger, no problem.
I can't thank
Gotta
you.
let go of my hand. I got a
Please,
vision.
please,
Roger, Roger.
Again,
Roger,
thank you.
Roger, I can't expand it until you let go.
What do you guys want for dinner tonight? Pizza? Boring. I'm gonna go somewhere
Well, it sounds like this family could use a little walk on the wild side.
Then come on down to Rogers Spot, America's only family-friendly dive bar experience. Pretend you're a barfly by resting your weary rump buttholes next door. That's altitude. Or is it? Kidding. I have to say that. And there's never a dull moment with bar fights every hour on the hour.
You showered with my wife! Rogers Spot.
I'm right, and I'm famous for saying, dive on in! Hey, look at you sitting there on the couch looking all sexy. Makes me want to dive on in!
Roger, you're home now. You don't have to say dive on in.
Sorry, with the 300 ribbon cuttings, it's a little hard to turn off, dive on in.
Roger, it was one thing when you were working yourself to death for the bar you love. But now you're just wearing yourself out promoting something that you don't even believe in.
Francine, relax. Have a drink. Dive on in.
Roger?
Francine, if I was doing the wrong thing, would they have invited me to the keynote speaker at this year's Emerging Titans of Industry Corporate Synergy Fest?
I don't know what that is.
And why would you? That's my limo now. Different from the one that dropped me off. Nicer, more promiscuous driver. Okay, Francine?
Don't say it.
Dive on in.
I'm quite a bit of thin set, so I'm gonna go ahead and lay quarter-inch back aboard. Great, I'll get going on the groundwork. Nice, Barry. Charlotte's gonna love that clean cutting.
Thanks, boss. Hey, Toad, Johnny still dragging their feet on the pavement?
Offering to remodel Charlotte's bedroom is a real stroke of genius. She's gonna want us so bad.
Wow, this room looks really great. Oh, when you're done, come find me so I can show you my appreciation.
Told you this would work.
Now, let's talk batting order.
I go last!
Hey, Roger! Nobody touches this shit. Oh, no, it's okay. Nick is a friend from before the money. How you doing, Nick? You come to see me speak?
No, I'm here for my AA meeting.
Over? Can't be. Nick, that's not who you are. You're a barfly.
Well, the good news is the state's going to let me see my daughter for the first time in 7 years.
How is that good news?
It's go time, Roger.
And now, let's welcome to the stage the founder and a partial profit participant of Rogers Spot, Roger Smith.
Thanks, Linda. And I said that. Okay, people, are you ready to dive on in? I can tell. Betty Crocker, Caleb Amos, John Deloria. What do they have in common? They're all entrepreneurs whose stories I haven't fully researched. You know, Rogers Spot wasn't always one of America's highest revenue-generating casual dining experiences. It actually started out as the kind of place where you could trade your child support check for booze. Hey, Mick's here! Mick, stand up! Mick was there at the beginning of the dream.
All right, what do you guys think of this one? Good, bad, ugly?
We probably don't, because in all 480 locations, it's just a stupid corporate fan. That's right. You lost.
Not bad.
We became Rogers.
What is that?
Yeah, but it's all for the best. Shut up, Nick. That's just for clarity talking.
Hard, not bad to hard.
Just like I was having. I'm running my car.
I'm not sure, Rebecca, if you're going for hard or not bad on the double arrow there. All right. So let's see. Let's get into this passage and see what we got. So we got the first paragraph, thermodynamic cycle, transfer of energy in forms of changing temperature, work, heat, work. So we got Q and W they're defining. One cycle do not alter so the changes in that heat and work after one cycle do not alter the internal energy. That's an important statement because they're telling something about not changing something. Not about changing something, but not changing something in a closed system. So clockwise is a heat engine, counterclockwise is a heat pump. moving initiatives or defining things. So it sounds like in paragraph 1 anyway, they're sort of setting the stage for closed systems. So closed systems and energy changes, whatever, about heat pumps and the heat engine. So that's the stuff I'm like writing down on my scratch paper is my notes for that paragraph, because I needed to find something in there. Excuse me. So next paragraph, heat engines. So they do a temperature gradient between a heat source and a cold reservoir. And works with the body. So there's another new term, working body or fluid, for some of the heat energy to work energy. The thermal efficiency, eta, is mentioned. So we got hot temperature and cold reservoirs. In absolute temperature, when it says absolute temperature, what does that mean, absolute? Kelvin, yes. I guess it's question 5 got some people because they forgot to convert to Kelvin. And then the cold reservoir on Earth, anyway, is going to be ambient environment, temperature of the ambient environment. So, that was a dense paragraph, but all in all, it's telling me about heat engines.
We learned a lot.
So heat engine and thermal efficiency come up in this paragraph.
Carry that with us the rest of our lives. It's not join the army. Ended up marrying his commanding officer.
Great.
Lieutenant
And then the next paragraph, an example thermodynamic cycle involves phase changes is the Rankine cycle, and has 4 stages. So, and it uses water as the working fluid.
As for me,
Great. 1, 2, 3, 4. Didn't read them. Didn't need them until later on. So paragraph 3 is just the Rankine engine, the Rankine cycle. Paragraph 4, steam turbine converts thermal energy to work by rotating turbine expanding steam goes to work. It's different from gas turbines, and the gas turbines extract energy from the combustion of a gas. Although the turbine entry of steam turbine efficiency of the two are comparable. So we're talking steam turbine versus gas turbine. This paragraph, again, note just what's in there. Don't have to make sense of it. Gas versus steam turbine. And then finally, the last paragraph. So this is a pretty dense passage. The working fluid decreases temperature in cooling towers or systems. So you can see the cooling fluid is a cold reservoir. Cool working fluid before the cycle starts. Water is often used as a cooling fluid. It's non-toxic, widely available, blah, blah, blah. The rate of heat to work is never 100% efficiency. Never 100% efficiency. Water vapor given off. Okay, great. So paragraph 4 is talking about the working fluid and the cooling fluid, the cold reservoir. So a lot of stuff in here. Holy cow. So overall, what's this passage about? What subject is it about?
Now, watch it, Roger. You know the rules. You want to leave the house, you have to wear a disguise. I know, but you left so quickly. My cape was still in the dryer. I panicked. Roger, there's a whole...
Physical thermodynamic cycles. The type of passage that we're looking at really here, it's just basically giving me new information. New info. I do like physics though. The question types in a new info kind of question are usually going to be those explicit question types that are like right there in the passage. There'll be a lot of refer back to the passage type questions. So that's what I can anticipate. So question number 1. Which of the following is always the case, that word sucks, but always the case for closed thermodynamic cycles? What did they tell me about closed thermodynamic cycles? They did give me some information here in paragraph 1 about closed thermodynamic cycles.
Right there, you know. Now scram. Speaking of.
Does not alter internal energy, which tells me straight up that in my delta E
Where are we going?
equals Q minus W, what's true? E would go to 0, Q must equal W. is 0, therefore Q equals W. So which two answers can I get rid of right here? C and D. So C and D go away.
Like he can't be by himself anymore.
I know. He even followed me to school one day. It was against
Then
the rules.
I gotta just, it's all in the sign convention here, isn't it?
Yeah, I can have
Net heat added, that's the same. Q is work done by the system or net done work to the system.
Get off. I need to go to
Is W by or to? As defined by our sign convention, work is, W is work done by the system. My answer is A. And there you go. A must be true.
I'm glad you're not
So a funny, kind of sucky terminology based 2 by 2. Question number 2. Stage 2 of the Rankine cycle is an example of A.
probably all that young tail.
I like these types of questions because they're usually just straight up right out of the passage. So I go back and I see step 2 is high pressure liquid is heated and vaporized at a constant pressure. Don't think too hard because it told you right there in the statement, a constant pressure. What's the answer? And the count of 3. 1, 2, 3. D, yay, isobaric. This one is, these are great questions, although sometimes people will overthink them just because you're like, is it really that easy? And yeah, sometimes it really can be that easy because it just said right there, constant pressure. Isobaric.
Through that crazy
I'm not going in there.
Then number 3.
But you deny me.
Okay. This is the pressure volume graph. This represents which of the following? The graph is for a heat engine or the graph is for a heat pump? What did they tell us about heat engines versus heat pumps? In paragraph 1, they told us that.
Of course. This is why I've been all worked up.
Hello? Is anyone in there?
They're telling us counterclockwise versus clockwise for heat engine versus heat pump. So clockwise is a heat engine, counterclockwise is a heat pump. Right there in paragraph 1.
I don't have a boyfriend.
So, is this clockwise or counterclockwise? It's clockwise. So if it's clockwise, which two answers go bye-bye?
Dan, we have something to show you.
C and D. Yep, you literally look at the arrows. Down and to the right, straight down, over to the left, up. That's a clockwise cycle. Clockwise.
It's an alien.
So that gets us the heat engine part. But then we got to deal with the 3PV versus the 13PV 6 over 6.
I think that's why.
They're really just asking us to do what? Find the area.
Oh, look, Dan.
Because the work done is the area under the curve. But since I've got a cycle, I can really just turn this into 2 triangles. It's going to be at least close enough to find it. So I've got this triangle and this triangle I need to find the areas of. Well, every triangle is 1/2 MV, or sorry, 1/2 base times height. So what's my base here?
Look, and Roger have a unique bond, Stan. Like you and me. Can't you see that?
Not 3, not 0, but 2V. 3V minus 1V equals
It's definitely an extraterrestrial spacecraft, sir.
Or maybe it's a refrigerator that fell
2V.
off an airplane.
You think everything's a
3V
refrigerator?
minus 1V. 3V minus 1V equals 2V. And what's the height?
And we will not rest until we find that something.
What if we get tired?
Tired? Did you know that P. Diddy only sleeps 4 hours a night? Like I've always said, when from the CIA.
5/2 minus 1V. 5/2 P minus 1P literally is 3/2 P. So that's the area of the first triangle.
We will capture this
Area of the second triangle, same deal. What's the base?
No. Tell us a little about yourself.
I like long walks in the blisters.
Again, 2V.
Playing the sulfuric rain.
What's the height in this case?
If you'll excuse me, I'm going to take upstairs.
2/3.
All over her.
We're going to have 1 P minus 1/3 P, so 2/3 P. So this is just not nice math, but I can do some simple canceling. 2 goes with 2, 2 goes with 2. So I'm going to end up having 3 halves P V plus 2/3 P V.
I feel like I can still hear it.
We are still here.
Without straining yourself too much, I bet you can tell the difference between this equaling 3 or not 3. Does this equal 3 PV?
So, you were in here last night?
No, therefore my answer is answer choice.
So horrible. Like looking at the ass of God. Anyway, I hope you enjoyed the show because it won't
There we go.
happen again. I am over.
So a couple questions. Clockwise versus counterclockwise.
We're doing it. She makes
Clockwise means the arrow's pointing clockwise. And that told us straight up in the first paragraph that clockwise is a heat engine, counterclockwise is a heat pump. Clockwise heat engine, counterclockwise heat pump. Right, Bridget? You're the one who asked that question?
All right. You're the oddball. Anyway, I'm not worried about mine. She knows things between us are totally cash.
Roger's the one.
Who asked the clockwise, counterclockwise question? Oh, Weston. That was Weston. Oh, that was a totally different question. I thought somebody asked clockwise versus counterclockwise. Weston's asking about
I see you started breakfast without
was
me.
it positive or negative work. I don't have to worry about positive, negative work here, actually, Weston, because I'm just calculating the area inside. I know it's positive work because I know it's the area inside the figure. To the right, it's positive, and going to the left, it's
I don't
negative.
know. I just knew that I know what it was when I found it.
Yes, everything inside here is the work done by my figure,
Yeah, she's terrific.
by my system. And then the change in volume is not 3, it's 3V minus V. I start at 3V and I go to V. That's a change of 2V, not 3V.
So, the thing is,
It's a delta, not
I
a
lived in the attic for a long time.
just what is the max. So this one's not a straightforward question, but it's not the worst question in the world.
Wait, what?
But don't worry. The idea is to make it reflect.
We make these to mimic what's on the MCAS.
Oh, that's actually
Number 4, coal is used in steam engines. Let's get rid of some illogical choices here, guys. It's coal.
I feel exactly the same way, but the opposite. We're breaking up.
What? Why?
Because I'm seeing someone
A's
else.
not a bad one. A's not a bad one because it's a working body. The coal might do work, but definitely cold reservoirs. Let's get rid of that. And is heat itself the heat pump? Or is it part of a heat pump? Potentially. Yeah, like C and D, they're illogical based on just our common sense of what is cold. I'm pretty certain I know what this is, right?
Don't tell me it's her.
What do you guys think it is?
Kathleen, wait! She's leaving, I swear! Right, you happy?
Probably the heat source. That makes the most logical sense. Let's just verify that.
If you just give us a chance, you'll know
What does it say the working body is? Like, where did we see working body in this thing?
Give it another shot. How about I take you to a romantic
Paragraph 2 is talking about the working body or fluid. So the transfer heat between the hot and cold reservoirs occurs through the working body. So is the coal serving as the transfer conduit of heat? Is it? What do you do with coal? You burn it. That's not transferring anything. That's producing heat. The transfer heat between hot and cold reservoirs. So what would the heat? What would the coal really be most likely? The hot reservoir, or the heat source. The working body, it even says repeatedly, the working body is probably a fluid. It's probably a fluid, and so heat source it is. In a steam engine, it would be literally whatever is transferring the heat from the coal burning to the water in the steam tank. So the working body or working fluid is the thing responsible for moving the heat from point A to point B. And that's defined by the passage, not as the heat source itself. A little bit of common sense has to come into this one, and a little bit of knowledge about what coal does. That's it's very oddly specific. And then finally, question 5. If the temperature of the fluid area turbine is 550 Celsius, what is the approximate theoretical efficiency of the cycle? What equation are we using here, guys? It gave it to me. Equation number 1. Eta is, and that's what we're trying to find. We're trying to find eta. Eta is 1 minus TH over TC. So I got to know, what is my TH? Oh, it's TC over TH. Sorry, thank you.
I don't care. Wyatt Gordon's company is the worst chemical dumper in the state. I'm not going to protect him after I become Attorney General. I'd rather lose.
What is my TH?
Bed with that devil. I'll be right back.
Is it 550 or is it 550 plus 273? Got to be working in absolute temperatures, so which means it's 823, which is 550 plus 273. Oh, that's the hard part. And what is my cold temperature? What is my cold reservoir? This came right out of the passage. You would not get the same ratio if it were not in Kelvin. You have to work in Kelvin temperatures. You must always work in Kelvin temperatures. It tells us that the cold reservoir is got to be ambient temperature if we're here on Earth. So ambient temperature, we figure it's close to 25 Celsius. 25 Celsius is what in Kelvin? Give or take 298. Those numbers look sucky. Let's make them nicer. How about 300 over 800? Does that sound a little bit better?
You have a plan for everything.
Yes, I do. Yep, I do.
1 minus 3/8, which is going to give me 5/8. So 5/8 is slightly more than half or slightly less than half?
It's one of those European style places, so we'll be doing down the hall.
Which makes my answer what? C. There we go. I don't want to actually turn that into a percentage because that's a sucky fraction, but at least I can tell if it's slightly greater than half or slightly less than half. And so, voila, I get 64%. Jackie, question.
Like I said, I would. I'll drop her at the bed and breakfast in 10 minutes. For a good time called, well, okay.
Ambient temperature, what should you always assume is standard conditions temperature, including in chemistry? 25 Celsius. 25 Celsius is your standard ambient temperature.
I always do the responsible thing. I'm Mr. Play.
Rosemary?
I just told myself, out of your box, Roger.
Or sorry, Rosemary.
Well, time to start living, because this just in, nobody was said on their deathbed, I wish I hadn't called that truck stop phone number. Oh my gosh, I feel like I'm rambling. I'm rambling.
Because the coal produces the heat in a steam engine. It is not converting, it is not transferring heat from point A to point B. Coal is not something that can transfer. It's a solid. It is not a fluid. And they were telling us working bodies or fluids do stuff. So being a solid, coal couldn't be used to do that.
Walk faster. I miss you.
I'm coming.
Because Caitlin, that is the definition of W. W is the work done by the system. You are all the way back to our definitions of things. That is what W is the work done by the system.
Out of the house and headed to that bed and breakfast. But it was me who called in the tip tomorrow. Who's gasping out there? Stop it!
Yep.
In the tip? Yeah, I tried to break up with her, but she wasn't.
Alrighty, so let's take a short break and we come back and we just talk about fluids. think about this question before we come back.
Never.
So let me start a timer, and I'll answer that question here in a second. So 10 minutes on the clock. Take a break, guys.
For a minute, and then a horn honk, distracting me. But that doesn't change the fact. To whom am I speaking? And to what
Diabetic.
am I saying?
Well, what does A mean in front of a word?
Right, got it.
Roger, where are you going? The bed and breakfast is the other way.
Yeah, there's been a change of plan.
What? Why? Are they overbooked?
No, I'm under it.
Without.
Listen,
Not neither, but without. And so it just means not diabetic. And diabetic is just a fancy word to say no heat transfer. Like, it's not a heated system.
no, you invested a little time.
Like, it's literally the straight definition.
$24?
The diabetic process is one with heat transfer. You're heating something, and a diabetic is no.
Super lady.
Blow it out your ass!
I have a feeling I'm gonna regret
Just because I'm closed doesn't mean I'm insulated. So insulated systems are going to be diabetic, but not necessarily closed systems. Isolated, insulated, but not closed.
We should arrive at the B&B in T-minus. Wait a tick.
It's a different ratio because I'm adding 25 or 273 to it. It doesn't scale linearly. If I say 25 over, what was it, 550? Do the math. 25 over 550 with a calculator is definitely a different value than 298 over 820.
You're losing in the woods. You'll be safe there.
Those are different ratios. You must always work with Kelvin. Got it, Rebecca? Kira, question? Or is that not a question, Kira? Oh, just checking. I saw your hand up. In fact, I believe if you take this 25 over 35, let me do it here real quick. You should get one of the other answer choices. That's what I would do. Totally would do that. I can make you tricky questions. One. Yeah, that would give me the 95%. If I use this, that would give me 95%.
Simple. I just have to pretend that I'm Dick Cheney and that helicopter is my friend's face. Not the most
I don't care if you see absolute or not. You always use Kelvin. If it didn't say absolute, you would still use Kelvin. If you do anything with temperature, you gotta use Kelvin. It's the way equations are set up, is to use Kelvin, not Celsius.
Alien steamer!
You came back for me. I knew you loved me. You know, people are going to ask us why we're back together. But I just feel like that's our business, you know? We don't have to explain our love to anyone. They're all just jealous anyway. Jealous that we have a kind of love that's greater than anything in the entire galaxy. And that's how I became Kim Kardashian.
And that's how she became Kim Kardashian. The end. So the change in energy would be negative P
P delta V. Work is always positive P delta V. Work is defined as P delta V. If I'm talking about the adiabatic system, the delta E is negative W. So yes, delta E is negative P delta V. Correct.
I hate it when people treat animals badly. Well, there's some really terrible animals out there. Just last week, some elephant tried to attack a poacher. Bad elephant. What? You can't be serious.
He sounds serious. I'd like to hear more. I don't have to hear more. I'll sign whatever you got, beautiful.
Hey, why don't we line up on that side for the petition and behind me to touch the hair?
I can't believe this.
Take a line, buddy.
No, you need to know delta E equals Q minus W, and then you can figure out all these by knowing what adiabatic and isothermic and all that mean. You can derive all of these other equations. I just got to remember delta equals Q minus W, and then what each of those means. You don't need to memorize all of those. That would be too much work.
I feel like that's Grand Broccoli. Someday I'd like to make it to the big city and couple with Dwayne.
Oh, you have not lived until you've been to Dwayne Reed. Dwayne Reed is magical. Oh, they have these divine mini nail clippers.
I need to hear this. There's a woman out front getting signatures where last week I was totally ignored.
Hey, look, it's DJ.
All righty, come on back, raise your hand, you're back and ready to rock and roll. You're not going to have to calculate a heat transfer for something under zeroth law unless they give you something like a delta equal Q minus W type scenario. That would be kind of an arbitrary thing to do. It's just defining, think of the zeroth law as a definition. Everybody else, Akshal, Alyssa, Ashley, Caitlin, Jackie, Caitlin, Kiara, Levita, Laura, Madeline, Sarah, Trevor, Anthony, Christina, Crystal, Danielle, Parker, Parth, Weston, come on back. Raise your hand when you're back and ready to rock and roll. This is the fifth. Holy cow, 35th. Saving attendance right here. And go. There we go. All right. Looks like we have a quorum. So, riddle me this. Why is it that helium-filled balloons actually float? Or rise, I should say. Because a lot of different things can rise, or sink, or float, but why particularly do helium-filled balloons rise? Okay, helium's less dense than air. What does that mean? Sure, there's less mass, but let's focus not on the area, but the mass. Float on the mass. As opposed to, say, an air-filled balloon, if I have a helium-filled balloon versus an air-filled balloon, then it literally weighs less, so it has less gravitational force than an equivalently air-filled balloon. Sarah, same question? Maybe not. No worries. So I have less mass for helium than I have for air inside that balloon. And so, but still, what is underneath it that's causing it to rise? What is the other force involved here? There's this other force that's called the buoyant force that's causing it to move upwards. And in fact, it's not because there's a greater or lesser buoyant force. In fact, between these two objects, the buoyant force is the same. As long as the balloons are the same size. So the buoyant force is the same for the helium-filled and the air-filled balloon. It's simply because of the mass. So these are the things that we're going to be discussing as how to determine buoyant forces, et cetera, et cetera. So first, to do that, we have to talk about density, because density did come up in our discussion there, right? And the density is simply the mass divided by the volume, basic unit, kilogram per cubic meter. Yes, kilogram per cubic meter, not gram per cubic centimeter, gram per milliliter. Another important value to know is what's called the specific gravity, which is basically the ratio of the density of something to the density of water. And in class number 1, we made sure to tell you that you have to know the density of water is 1,000. The density of water is 1,000 kilograms per cubic meter. When is it 1? When is the density of water 1? So in chemistry, when I'm using what units? Gram per cubic centimeter or gram per milliliter. Yeah. So you have to remember the density is 2 different units. 1,000 for physics, because it's kilogram per cubic meter. 1 for chemistry, because it's gram per cubic centimeter or gram per milliliter. And the last thing you want to keep really strongly in mind is this other derived thing, which is the weight of a fluid. The weight of a fluid. And normally we would say weight is just equal mass times gravity. But we don't measure masses of fluids, generally speaking, we measure volumes. So if I measure the volume of a fluid, how can I find the weight of that fluid? Well, volume is equal to, mass is equal to density times volume, so rho v g is the weight of my fluid. So this is a very used concept when dealing with fluids. Sarah, question? Specific gravity is unitless, correct? Because it's a ratio of densities. Are you asking, Bridget, what is G here? This is the gravitational constant. Yep, that is the same, because it's weight equals mg, mass times gravity, and that is going to be mass just substituted in with rho v. What's the density of water in kilograms per liter? It would be 1 kilogram per liter. And the Sheeta question? It's just another way to give you the density of something. Making beer. It's just another way to measure density. Often used in beer making, or what you might measure in liquor making of any sort. So it's just another reference point, another thing they can confuse you with. So when dealing with fluid statics, or urinalysis, that can be right too. Sheeta, another question? No? Yes? And specific gravity, just the ratio of densities. A different way to give you density. So when we're dealing with fluids, we're often dealing with hydrostatic gauge pressure. And that's basically saying, as I push my object below water, there's some pressure due to the fact that all of this cube of water is pushing down on the surface. So we're basically saying the pressure is that here it's 0, and as I go down, what's going to happen to my pressure? It's going to increase as I go down. Like if you go under the depth, under the swimming pool, under the surface of the swimming pool, you'll feel a greater and greater pressure on your head. That's what we're talking about, gauge pressure. And there's an equation that gives us that pressure. It is equal to the weight of the fluid, the force, the weight of that fluid over the area. Volume is depth times area. Areas cancel, so gauge pressure is just going to be density of whatever fluid is in this cube times the gravitational acceleration times depth. There's a trap built into this. There's a trap built into this. In many, many, many passages, what are they going to give you instead of depth? They're going to give you height from the bottom. They'll give you height here, and they'll give you total depth of the fluid, the body of depth of the body of water. So you might say this is 12 meters, and they'll say the height from the bottom is 3 meters. So what should you use in this equation? You got to use 9. So be very wary of that. That is a very common thing for them to do, is to flip over the problem. So instead of giving you depth, they may give you height from the bottom. The other trap with this is that what is the total pressure at this point? Assuming we're here on Earth and this is a glass of water, a swimming pool. That's right. The total pressure at that point is not whatever you calculate with this equation. It's pressure at the surface, which for almost all problems is going to be the atmospheric pressure plus the gauge pressure. So nasty little tricks are built into this problem. In fact, it's very common to bring up this graph. What does my gauge pressure graph look like for depth versus pressure? As depth increases, the pressure increases, so it's proportional. And as Ashley's telling us, it goes through the origin. At the surface, at zero depth, I will cross the origin. I'll have zero pressure. What does my total pressure look like? Everything's going to be shifted up. It's basically the same thing. It's parallel to it. It's just shifted up by 1 atmosphere. So very common for them to give you a graph or like asking you to pick a graph that says what is the total pressure or what is the gauge pressure. The origin is what your gauge pressure will cross the origin, your atmospheric or your total pressure will not. Bridget, question? No, what's the unit you're generally going to see here? Pascals or kilopascals, either one of those, which is why you need to know the conversion. So what is 1 atmosphere in kilopascals? (100 kPa). Wow, that was the worst K and P I've ever written in history. All right. So, what is buoyant force? What is buoyant force? So, if I'm looking at this object, what's the gauge pressure here compared to the gauge pressure here? The gauge pressure at the top is smaller than the gauge pressure at the bottom. So, to answer our question, the pressure at the top is less than the pressure at the bottom. Because there's just less fluid above the object than there is at the bottom of the object. Well, what does that mean if I've got a pressure differential like this? Remembering that pressure is always push. Pressure is always push. The pressure on the bottom will be greater than the pressure on the top, which means I'm going to have a net force upwards. And that net force upwards is called the buoyant force. The net force upwards will be my buoyant force. So when I'm in any body of fluid, I will actually experience a buoyant force. And what could be fluids? What could be some fluids I'm dealing with here? A liquid or a gas, including, don't forget, the atmosphere. The atmosphere is very much a body of fluid that we could be talking about. So how do I determine the buoyant force? It is going to be rho of the fluid times the volume of the submerged object times, and there's a missing variable here, G. So I take the density of the fluid in which this object is submerged, not the density of the object. So rule number one, don't insert the density of the object here. Not the density of the object. Number two, when I say volume submerged, it means what if this object were here at the surface? Would the volume submerged be the volume of the object? Not at the surface like this. That's another trap. So the volume submerged is not necessarily the volume of the object. And then G is just G, gravity, gravitational force, or sorry, gravitational acceleration. So what can we do with Archimedes' principle? So let's see what the net force on my rubber ducky is. Rubber ducky, make that time lots of fun. The volume submerged is how much is underwater. How much is underwater? They'd have to, no, it's not zero, it's how much is underwater. They'd have to tell you that this has 20% submerged, or 30% submerged, or 100% submerged. It's got to be whatever's actually under the surface. They can't just leave it to gods for you to figure out. So, what is my net force on this rubber ducky at this point while it's sitting here on the surface? Ah, yes. When we're floating on a surface, the net force is going to be zero. Because is the duck rising, or is the duck falling, or is the duck just in equilibrium? It's in equilibrium, which means the buoyant force and the weight must be equal. So whenever, this is called what's called neutral buoyancy. Neutral buoyancy. Whenever you've got an object that is neither rising nor falling, the buoyant force is equal to the weight. And we can always say that, since the weight is equal to the buoyant force, the weight, which is rho of the object, volume of the object, gravitational force, is equal to the buoyant force, which is density of the fluid, volume of that object that's submerged, times the gravitational constant. Gravity cancels out, and rearrange it just as SCAD, and we get this wonderful relationship. Says rho of the object divided by rho of the fluid equals V of submerged divided by V of the object. The take home of this relationship is this. What is rho of the object divided by rho of water? What is rho of the object divided by rho of water? It's not beer, but it's related to it. Talk about is a unit, not a unit, a thing. It's the specific gravity. It's the specific gravity of the object. And that's going to equal what? The volume submerged divided by the volume of the object, which is the percent submerged. Yes. So percent of my object submerged. So this is a fantastic thing. Like it's a lot of questions that hinge on this one concept here. Oops, I didn't want to change that blue. Well, if I tell you that an iceberg floats 90% submerged, most of the iceberg is floating underwater, then what is the density of said iceberg? Its specific gravity is 0.9, which means its density is specific gravity is 0.9, and we're looking for density divided by the density of water, which is 1,000. New density is going to be 900 kilograms per cubic meter. That makes a lot of questions become very, very, very much easier. So if you know the percent submerged, you can tell the density of that object simply by multiplying by 1,000, multiplying by 10 in this case, but 0.9 times 100. Sorry, 0.9 times 1,000. 0.9 times 1,000. So it's a nice, easy way to figure out how dense something is. And that's why we use densitometers. That's actually the concept of densitometry, which is what I think Bradley is so excited about with beer. I know it's Kevin. That's what he's using, is this concept of submerging a densitometer, that the depth by which it's submerged tells us the density of the beer and tells us how much alcohol is in it. Are we with me, Smiley Browning? All right. So let's try a practice question. Which is probably the best explanation why a helium-filled balloon rises, whereas a air-filled balloon sinks? A, B, C, or D? What do you guys think for this one? Now I have that stupid song stuck in my head. Rubber ducky, you're the one. You make bad time lots of fun. Rubber ducky, I'm awfully fond of you. Gotta love Sesame Street. No, I might be Kermit the Frog, though. Hi, well, Kermit the Frog here for Sesame Street News. Today, we're going to be talking about floating objects. So, anyways, looks like most of us are saying D, which is the trap. Which is the trap. It is totally a trap. Because if these balloons are the same size, remember, what is buoyant force? Density of the fluid times volume that is submerged times G. So the density that these things are submerged in, is that any different? No, they're both submerged in the same fluid. The volume that is submerged, that's the same size balloon. G is different. The buoyant force is the same for both objects. But what is it that's different? Going all the way back, and Sarah remembers going all the way back because of this first thing we talked about. It's the weight of the balloons. The downward force is different because a helium-filled balloon is lighter, an air-filled balloon is heavier. So, which is the best answer? Well, we know it's not going to be helium is warmer. That's weird. It's not going to be helium is a noble gas. That doesn't really have anything to do with it. It's not going to be force up that's different. It's the gravitational force. It is the most common trap, by the way, when it comes to fluid-based questions. Very, very, very common trap. When it comes to buoyant force, you got to remember, the buoyant force is usually not the thing that's changing when they're doing comparison questions. It's probably going to be the mass of the object itself, the gravitational force. That's so rude. All righty. Questions? Smiley Frowny. All righty. Well, let's now talk a little bit about flowing fluids, fluids that are moving through a tube. So fluids fluids that are moving through a tube follow this rule. We have the flow rate versus flow speed. Flow rate is the volume per unit time that's moving through a system, so cubic meters per second. Flow speed is the linear flow in meters per second, and the flow rate is equal to the area times the linear speed, the velocity through it. So if I'm looking at a tube like so, it's wide here, it's narrow here. This is my flow speed in, this is my flow speed out. What is true about the water that goes in here, the volume of water that enters this tube here, and the volume of water that leaves the tube here? What must be true about those? It must be the same. Volume in has to equal volume out. Volume in must equal volume out. That is a rule that we need to always remember for ideal fluid flow. Bridget, question. Yes, because the air is a fluid. The air is a fluid. The atmosphere is a fluid. Gases and liquids can both serve as that in that capacity. So, for an incompressible fluid, which is what we need to always be talking about, volume in equals volume out. So, that tells us something. Since A1 is bigger than A2, what must be true? V1 must be bigger or smaller than V2. V1 has to be smaller than V2. V1 has to be smaller than V2. And you've experienced this every day in your life in some way, shape, or form. Like if I put my thumb on the tip of the hose, what happens to the water? It comes out faster. It shoots halfway across the eyes. You can spray your little sister with it or your little brother with it, whatever. So it's going to come out at a higher speed, which means it's going to go farther, all that fun stuff. Or if I am going through the narrows in a raft or something like that, that's where the water's moving more quickly. That's where the fun is. That's where the rapids are when you're going whitewater rafting, when you're in the narrow part. So, the equation of the rules, this is what we call the continuity equation. A1 times V1 equals A2 times V2. Now, there's a nasty trick biologically that comes up. The area of the aorta, cross-sectional area of the aorta, versus the cross-sectional area of the capillary bed. Which one is the aorta? Which one is the capillary bed? Brenna, why is A2 the aorta? Bell, why is A2 the aorta? Exactly. The capillary beds, all taken together in the body at the same time, have a much larger cross-sectional area than the aorta does. And this is why this is a bit, like, a lot of times people interpret this incorrectly. They think that, oh, the blood must be just flying through the capillaries because they're so narrow. Well, that would be completely bad. If the blood was flying through my capillaries, then none of my nutrient exchange would have time to happen. So the aorta is where the blood's moving more rapidly compared to what's going on in the capillary beds. Because as a whole, the area of the capillary beds is freaking huge compared to the aorta. And so you've got to remember that relationship there. Because otherwise, you're going to get really confused on what's going on biologically and what's going on physically. Are we with me? Smiley frowning. It's a subtlety, but it's an important subtlety, remember, to connect biology with physics. just because of that, though. But there's a couple things actually going on there, Bill, to address that a little bit more. If we put pressure into it, the air is also where the pressure is the highest, the capillary bed, the pressure is the lowest. So there's also effects there as well. However, if we're just thinking in terms of relative size, the aorta is smaller than the capillary beds. So we're not taking all things into account here. There's a lot more. It's a lot more complicated, unfortunately. Alrighty. So, what do you guys think of this question? A, B, C, or D? Radius of the heart decreases by a factor of 10. What happens at low speed within? So is it going to decrease or increase? So we should be able to get rid of C and D because we went to a narrower pipe. Is it going to increase by a factor of 10 or a factor of 100? It looks like we're about 50-50 there. It's going to be 100. And why is it 100? Because it's not like kinetic energy, but we're talking radius, and the factor is going to be area. Area is r squared. Area is r squared. So it has to increase by a factor of 100 because I'm going to a narrower tube. The narrower tube is the one in which it must go faster. If the area drops, then the velocity must increase. And if I have area, I've got to do it by radius squared. There you go. That's a common trap as well, to be radius when it's actually area that's important. Or how about this one? Pipe splits into two pipes, each to half the original radius. What is the ratio of flow speed in the original pipe to the flow speed in each branch? All right, looks like we're fairly mixed all the way along, but I'm starting with a large pipe. Let's say it has a radius of 1, and it's splitting into two pipes, both of which are radius of 1/2. Flow in my one side has to equal what? I gotta add. I gotta take the flow of 1/2 plus the flow of 1/2. So it's gotta equal flow out. So both of these have to add up to this flow. So what's easiest here is actually, why don't we just run some numbers? Let's say my radius is 1. I'm gonna have 1 squared times pi times V1. And over here, I'm gonna have squared times pi times V2, and since there's 2 of them, I'm going to multiply by 2. So it looks like the pi's cancel out. The 1's not going to be an issue. So I'm going to have V1 equals 2 times 1/4 V2. What's 2 times 1/4? 1/2 of V2. So what's my answer? Is it B? Nope. Is it D? Can it be D? Nope. It's either got to be 1/2 or 2. So I'm going to take the flow speed in the original pipe, V1, which is 1/2 of V2, and divide it by V2, which is just V2. And so what's 1/2 V2 divided by V2? That is just 1/2. A is my answer. So you got to be careful here because it's the ratio. It's the ratio of V1 over V2. V1 is equal to 1/2 V2 over V2. So 1/2 is my answer. It's a little trickier question just because there's not a lot of info given. So make up some numbers and run the scenario. Are you with me? Smiley frowny. All right. Now, when we're talking about fluid flow, there's some rules that have to be obeyed. And number one is the fact it's got to be incompressible. We already mentioned that. So rho is going to be constant. Density is constant. It's got to be not really viscous. Negligible viscosity means we're not dealing with syrup here. We're dealing with water, alcohol, blood, not syrupy, gooey crap. It's got to be following streamlined flow. And what we mean by streamlined flow is everything moves together. There's no eddies, no weird whirlpools and crap like that. This is what's called turbulent flow because things are going woo, spinning out of control. Particles are moving past other particles. Laminar flow, never cross the streams. And we have a steady flow rate, which means I don't have any leaks. I don't have any valves putting stuff into this. So that again adds to the volume in equals volume out. So if you have a broken vessel, then that's not laminar flow, that's not flow steady, that's not ideal fluid flow. So the reasons why this might not work. Will a gas behave ideally when it comes to being a fluid? Will a gas behave ideally when it comes to being a fluid? No, because it is compressible. Will syrup or molasses act ideal? No, it is all gloppy and will not flow properly. And if I'm talking about like let's say wind in a storm, will that be behaving ideally? No, because I've got turbulence. Gases don't necessarily have to be turbulent. They don't necessarily have to be turbulent. There is one gas, by the way, that will act sometimes turbulent, but act sometimes ideal, and that's the one we can't really change it, and that's the atmosphere. The atmosphere can behave ideally as a fluid. Because I really can't change the atmospheric pressure. I mean, that's a fairly constant thing. Syrup has high viscosity. Molasses has high viscosity. It does not flow nicely. It flows gloppy. And the rule to bind all of this together with this ideal fluid flow is called the Bernoulli's law. Although it looks really scary, it's very simple. You probably don't have to memorize it so much as this is just the law of conservation of energy for fluids. For fluids. So So I got pressure on one side times, what's this the equivalent of? What kind of a term is this energy-wise? It's like my potential energy. It's just like MGH. It's rho g y1 being its horizontal displacement. So that's like my vertical displacement. That's my potential energy. What's the 1/2 rho v1 squared term? Kinetic energy. So I'm basically just saying potential energy 1 plus kinetic energy 1 plus pressure 1 equals pressure 2 plus potential energy 2 plus kinetic energy 2. Conservation of energy of fluids. There's two scenarios that they run more often than not with this equation. The first is at 2 points of equal height. If I'm talking 2 points of equal height, which term disappears? Potential energy term is going to go away, which means the pressure is related to the velocity. The most common example, my wing. As the air approaches, and we can assume these are roughly the same height where it enters and leaves the wing, so these terms disappear. Since the air does not have to go as far down here versus up here where it has to go farther, we see that the air goes faster above the wing than it does below the wing. Since these have to equal on both sides, if the velocity above is faster and the velocity below is slower, what must be true about the pressures? The pressure above the wing has to be lower than the pressure below the wing to make this all equalize. So that is why a wing can allow us to fly, because I'll see a lower pressure above the wing and a higher pressure below the wing. And whenever I have a pressure differential, I will see there'd be a net force upwards on this thing. So that's one of the common scenarios where you have same height, the potential energy term cancels out, and therefore you can do pressure versus velocity. The other common scenario is this one. Any fluid exposed to the atmosphere is always going to be atmospheric pressure. So if I cut my carotid artery, so I cut my body and I've got a carotid artery bleeding out, what's the pressure of that fluid as it comes out? It's 1 atmosphere. What's the pressure of the fluid inside the body? Well, it's high. You've got a high pressure pushing it, right? So you got the blood just gushing out. You have a pressure behind it exposed to the atmospheric pressure, and blood's going to shoot out. So any fluid exposed to the atmosphere, there's a net pressure pushing that blood out. That's why if you cut your arteries, you bleed out quick. You cut a vein, veins may not even bleed. Veins don't have a pressure behind them. They're equalized. So, two common scenarios that we run into here. So, what exactly do conservation of volume and energy for ideal fluid mean for real biological situations? So, let me run a few scenarios here. Since the capillaries are much smaller in the aorta, is the blood flow faster in the capillaries? And no, why not? Capillaries arteries as a whole have greater total area? So the answer here is no. In the carotid artery, the blood is exposed to the air, is under pressure, but at the point at which it's cut, it's exposed to the atmosphere where it's only atmospheric pressure. So I have a pressure that's higher than atmospheric pressure behind it, thus pumping the blood out of the body. You had to do the sound effect thing, right? Yes, that's actually a good point to make. When we're measuring blood pressure, by the way, guys, the pressure in the vessels is actually going to be atmospheric pressure plus the blood pressure that we measure. Because, like, yeah, what's your blood pressure? It's like 120 over 80 or something like that. But for me, it's like 140 over 90. But don't count my high blood pressure. That's above atmosphere. That's above atmosphere. Because everything in our bodies is basically held at atmospheric pressure for the most part. And then, last question, then we'll do a passage. I know we're running tight on time, but this one passage won't be too bad. How do blood pressure compare in the arms and legs? Ignore distance from the, or don't ignore distance from the heart, I should say. Why is it generally higher in the arms? Even though you might think it's at a greater height, it might actually have a lower pressure. It's closer to the heart. So basically the whole point here is Bernoulli's law, arms are higher. A little bit, not by much, but like in your arms, it tends to be a bit higher than in the legs. That's why we have problems with like getting blood back to our legs and poor circulation in the legs, but we generally don't have poor circulation in our arms. The arms are generally higher pressure because they're just simply closer to the heart. So what does that tell us about Bernoulli's law and biological systems? It's not really directly applicable. There's a lot of differences because you got biological differences you have to deal with. So Bernoulli's law, you just got to be careful. Don't apply it blindly to biological systems because otherwise you might be forgetting some very important things. So don't apply Bernoulli's law to blood flow directly. It'll help you explain certain things, assuming this is zero and assuming that's zero and assuming this and that and the other thing. But really, don't generally apply Bernoulli's law to blood flow. That's the take-home point. Alrighty, let's do another passage. So let's do passage number 7 on page 74. Raise your hand when you're ready to rock and roll on this thing. It's a really short passage. It's only 4 questions. One of the few passages we run into an ICC like this, but this is possible on an MCAT, by the way. Passages range from 4 to 6 questions in the science section. So I'm going to give you guys on this passage only 6 minutes. Yes, only 6 minutes. Because that's 1.5 minutes per question. So I'm going to give you 6 minutes to do this, guy. On your marks, get set, and go. everybody. What do you guys think? Good, bad, ugly? Better than the last one? Structure-wise, this was definitely a simpler passage. Not as much going on in it. So let's get in there and check. So an object moves through a fluid. So object in a fluid. So it tells me we're talking about fluid statics or fluid dynamics, one of the two. And there's friction, drag force, and viscosity. Viscosity is IMF, and it's temperature dependent. So they're just telling me about a little bit about my fluid. And so paragraph 1 is just really just setting up the stage for fluids and drag. Then I got my next paragraph, when a spherical object falls under the influence of gravity through a fluid, the magnitude of the viscous drag force is given as Stokes' law, where N is the coefficient of friction, now viscosity, R is the radius, V is the instantaneous speed. The submerged object also feels a buoyant force, B, where rho of the fluid is the density, G is the magnitude of acceleration due to gravity. Both the forces Fd and Fb oppose the gravitational force Fg. When the descent speed is sufficiently great, the net force on the object drops to 0, and it falls at a constant speed known as the terminal velocity, given by blah, where rho v. So we got basically one giant paragraph defining 3 things. Defining for me drag force, buoyant force, and terminal velocity. And they also told me a relationship that said drag and what other force counter buoyant force. Sorry, drag and buoyant force counter what other force? The gravitational force. It says it right there. All right, then the next paragraph, kinetic molecular theory, can be used to viscosity of ideal gas, M, K, constant, T, delta, C. So this basically is giving us crap tons of equations here, aren't they? So paragraph 3, just viscosity. And then paragraph 4, I'm not even going to hashtag that one, they're just giving us some constants. Air, ideal gas, 20 Celsius, density, viscosity. So a fluid passage is basically just giving us, again, new info, which means I'm going to get a lot of explicit questions. It's just straight out of the passage, according to this, according to an equation. So that's how we do this one. So bam, 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 do a quick highlight, get through it. Answer questions. Number 1, if an object falling through the fluid at speed less than its terminal speed, which of the following best describes the relationship between magnitude, drag force, buoyant force, gravitational? Caitlin, is that a question? Maybe not. So which 2 forces must be on one side, which force must be on the other side? Buoyant and drag have to be on one side. So that means C and A are bad choices because it said explicitly in the question that buoyant and drag force counter the gravitational force. And if it's falling at a speed less than its terminal speed, which means it's going to be accelerating, which force is going to be greater? Gravity or buoyant plus drag? If it's still speeding up, it's going to be gravitational force is greater than the other 2 because I have a net force downwards, which makes this thing accelerate. So, nice little 2x2 to start things off. Nice little 2x2. No, it won't be. B wouldn't ever be true because that means it would be going up. The gravitational force bigger than the buoyant force and the drag force means it would be shooting upwards. But, or at least slowing down. This object is falling down under the force of gravity. It is accelerating downwards. The buoyant force and the drag force are upwards. It's not at its terminal speed, which means it's still accelerating, which means there's still a net force downwards on this object. Net force downwards on this object. They're telling us in the passage about terminal velocity, which says that's when there's no net force. The best we can hope for is for these things to be equal. Everybody got it? Ashita? Yes, that would be when they would be equal, because the net force would be 0. That's what they're telling us in the paragraph, but they're like taking us back to not that by saying it's less than its terminal speed. Question number 2. Which of the following ball bearings would have the fastest terminal speed? Well, basically, this is just having to do a 2x2 with the equation. Large, small, more dense, less dense. That's really what we're being asked about. So, what's my terminal speed? Right there. Large or small? Which one's going to have the greater terminal speed? Large, because it's proportional. So we can get rid of small. All right. Is it going to be the more dense or the less dense? More dense, because density is in the numerator. So, is that going to be the gold or is that going to be the steel? That's going to be the gold. It's gold. So gold is my correct answer. D is the correct answer. Large gold ball bearing has the higher density and the larger size, which will both increase my terminal speed. Alrighty, so another 2x2. 2x2s, yay! Number 3, another 2x2. Are you kidding me? Yeah. An air bubble rising through a calm liquid also feels as you crash forwards, blah, 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 blah. But this time we're going upwards. It's like we're falling up. We're falling up. So which two answers are probably unlikely? Gosh, stop. C and D, the ones that take out the two densities completely are the unlikely pair. Because it's got to be at least like the original. Well, which one is the original? A is the original. B is kind of like the flip-flop, the mirror image of the original, right? So, which one's the more sensible one if my bubble is falling upwards, effectively? Is it the original equation or the flip-flop equation? It's the flip-flop. Because to get the right sign on my terminal speed, in fact, if the density of my fluid is now less than the density, or the density of my object is now less than the density of the fluid, this is the only way to get a positive sign for my terminal speed. And speed, notice it's speed, not velocity. Speed must be positive if it's moving. So it's got to be B. Erica, question? It wouldn't be solving for anything, really, because the difference between the densities is what's required to find the terminal speed. Bradley? speed, which is it's telling us, well, here's the trap of it. If Arduino's raised, and we're trying to find the bubble's terminal speed, speed is going to be positive, because what does a negative speed mean? Going opposite the direction of its normal wanting to go that way. This bubble wants to go that way, so we need to have a positive speed. This would give me a negative speed. If we're talking about terminal velocity, then the negative would make more sense. Right, but now the direction, the standard direction of motion has flip-flopped, which means we still need to define it in terms of positive speed. Because that positive speed must be interpreted as going upwards. It's a subtlety in the phrasing. And really, just think of it this way. If it's scalar, it's going to have to be positive. If it's scalar, it's going to have to be positive. All right, number four. Number four. In the Winter Olympics, another 2x2. Holy crap, 2x2. About, well, what are we really looking at here? Viscosity, right? So it's equation 4, all right? So we got cooler, warmer, and higher, lower viscosity. Well, first off, who's going to have the advantage? Higher, lower viscosity. Lower viscosity. So we can definitely get rid of the B and D. Higher viscosity is lame. So then, when's that going to be true? Look at our viscosity equation, and we see that if temperature goes up, what happens to the viscosity? Gotta go up, which means which answer is the bad answer choice? C is the bad answer choice. We don't want to be warm, we want it to be cold. A. Now, some of you may have actually picked C because you were thinking about this in terms of chemistry. If you increase the temperature, then viscosity goes down, doesn't it? But that's not for gases. If you increase the temperature, viscosity decreases for liquids. But if I increase temperature, viscosity increases for gases. It's different. Liquids have a different relationship than gases. So you got to use the equation to help you out on this one. Of an ideal gas. Alrighty, that's it for the passage. That's it for class tonight. I'll stick around and answer questions like I always do. Answer questions till the end of time. And let's do it. Let's do it. Why does hot air rise? Hot air rises because of the fact if I have a hot air balloon, that means the hot air is going to be less dense inside the balloon, which means the hot air balloon would be lighter. Same reason why helium would rise. Caitlin, question? For one, how does the speed less than terminal speed denote acceleration downwards? Because what does it tell us about terminal speed in the passage? It says that when the descent speed is sufficiently great, it'll reach the terminal speed. So as my object is accelerating downwards, it's getting faster and faster and faster and faster until it reaches similar velocity. And what's forcing it to go downwards? Gravitational force. Gravitational force has to initially be greater than either one of those. Well, I hope it went better than it did last time because I jacked up hardcore last time, so thank you, Bell. You'll certainly see a fluids pass, or something with fluids, and probably something with redox chemistry of some sort in every test. Yes. We're just literally closer to the heart, Caitlin. My blood is not as far from the heart in the arms as it is in my legs. And so the pressure from the heart is going to be higher. Pressure drops as you go farther from the heart because it's pumping.